Hello class, today we are going to continue our study of probability and we're going to look at the difference between independent events and dependent events. Now first off, independent events. This is when one event does not affect the other one. So for example, if you're going to flip a coin and roll a die, it doesn't matter. Doesn't matter if you get heads or tails, you still have options of 1 through 6 on the dice, right? Doesn't matter. So those are independent events. Okay. Now, two events, call them A and B, are independent if and only if the probability that both events occur is the product of the probabilities of the events. Okay. So the probability of A and B is equal to the probability of A times the probability of B. All right. And that's how we're going to do stuff with independent events. We're going to take a look at this really quickly. Let's open this up. Okay, as example 2 because there is no example 1, because, I don't know. Anyways, so we have a group of 4 students, includes 1 boy, 3 girls. The teacher is going to randomly select one of the students to be the speaker of the group and a different student to be the recorder of the group. We're going to use sample space to determine whether randomly selecting a girl first and randomly selecting a girl second are independent events. All right, so we need sample space. We've got to write our sample space. So as you remember, this is the list of all the possible outcomes. So let's just start listing them out. We could get girl number 1 and for the speaker and the boy for the recorder. Or we could get girl number 2 and girl number 1 for the speaker and girl number 2 for the recorder. Or girl number 1 and girl number 3. Or, alternatively, we could end up with girl number 2 and the boy, girl number 2 and girl number 1 for the recorder, girl number 2 to speak, and girl number 3 to record. Right? Or we could have girl number 3 could be the speaker, boy's the recorder, girl number 3 is the speaker, girl number 1 is the recorder, girl number 3 is the speaker, and girl number 2 is the recorder. Or the boy could be the speaker, and we have girl number 1 for recorder, or boy and girl number 2 for recorder, or boy and girl number 3 for recorder. Okay, so here's all the possible outcomes. Let's take a look and see. First, we want the probability that the girl is speaking. Okay, so probability that we select a girl first. So I'm going to probability that a girl is first. First one chosen is a girl. And we need this would be times the probability that a girl is chosen second. So girl is second. And if these are independent events, this will equal the probability of both. Probability that we have both. So we're going to have a girl first and second. Second. There we go. Both. So probability that we get a girl first, that would be right here. Probability. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 out of 12 total possibilities. Probability that a girl comes second. Well, let's see, that's not going to be those 3 there, so we have those. So that would be, again, 9 out of 12. All right, and the probability that both of them are girls, that is going to be, let's see, not those 3, those are boys, not these 3, those are boys, so we just have those right here. So that would be 6 out of 12. All right, so does this work? Let's see, 9, let's go ahead and simplify this. 9 12ths, that's would be 3/4 times 3/4, which equals 1/2. And no, it doesn't. 3/4 times 3/4 is 9/16. It is not 1/2. Does not work. And so, since it doesn't equal, these are not independent. Not independent. Not independent events, because the probability of the first one times the probability of the second event does not equal the probability that both events happen. All right. So, and the reason for that is because if you choose that girl first, you can't choose that girl to go second, can you? So who you pick first determines, it has an effect on the second event. So those are called dependent events. When the occurrence of one event does affect the occurrence of the second event, then they are dependent. All right? And the probability that an event B occurs, given the probability that event A occurs, is called conditional probability of B given A. We write it like this. This means probability of B given A already happened. Okay? So the probability that the second person was a girl, given that the first one already was definitely a girl. Okay? And the way this works, all right? Okay, if two events A and B are dependent, then the probability that both occur is the probability the first one occurred given the second one occurred. So, like this. The probability of both A and B equals the probability of A times the probability of B given that A already happened. So, let's use the example we just looked at with the girls and boys, right? So, probability that a girl is first and second is going to equal the probability that a girl was chosen first. So let's see, probability that a girl was chosen first, that would be not those three, right? We just have these 9. So 9 out of 12 times the probability that a girl is second, given that we picked a girl first. So now what we're looking at is the probability that a girl was picked second, given that we're only looking at the ones where the girl was picked first. So that's just these 6 out of 9. Okay, so the first one was 9 out of 12 because that's that the girl was chosen first, and all of those were for that, right? But then, given that we're only looking at these, what's the odds that we get a girl second? Okay, and so you end up with that. So 9 over 12 times 6 over 9, which is going to equal 1/2. 6 over 12, 1/2. All right, so that is dependent events. That can be a little bit weird, a little bit tricky. Got to remember, given the first one already happened. That's what's important, though. Okay, so let's take a look at some more examples here. Okay. As part of a board game, you are going to spin the spinner, which is divided into equal parts. Find the probability that you get a 5 on your first spin and a number greater than 3 on your second spin. So, first question we have to ask, is this dependent or independent? Does what I spin the first time change my odds for the second spin? No, they don't change your odds. That would be silly, right? Because all the numbers are still there. We haven't taken anything out. So this is going to be independent, which means the probability of getting a 5 times the probability of getting anything greater than a 3. So that would be anything 4, 5, 6, 7, or 8 is going to equal the probability of both. Probability of A and B. Probability of this and the probability of that. That's what we're looking for. All right. So the probability that we get a 5, well, there's only one 5 and there are 8 numbers, so this would be 1 out of 8. Times the probability that we get 4, 5, 6, 7, or 8, anything bigger than 3. So 1, 2, 3, 4, 5 out of 8. 5 out of 8. And that equals, well, 1 times 5 is 5, 8 times 8 is 64. That does not simplify, so it's 5 out of 64. Or, as a decimal, this is approximately 0.078, which as a percentage is approximately 7.8%. All right. Any of those are good. It just depends on what the question is asking for. All right. Okay, so let's take a look at this. We have a bag of money. We've got 20 $1 bills and 5 $100 bills. Well, we want to know what if we randomly draw a bill from the bag, set it aside, and then randomly draw another bill from the bag, what is the probability that both events A and B will occur? So event A, the first bill is $100. Event B, the second bill is $100. All right, so if I draw a $100 bill out of the bag, does that change the odds of getting another $100 bill, right? Well, yeah, because I don't have as many in the bag now, right? So it's not going to be the same. So the first bill, there's 5 of them, $500 bills. So 5 bills that are good. And we have how many bills? Well, we have 21s plus 500s, so we have 25 bills in the bag, right? So the first bill, my probability is 5 over 25, which does reduce to 1/5. Okay, that's event A. Event B, I'm going to get another $100 bill. Well, now that I took this one out of the bag, remember, this is probability of A times the probability of B, given that A already happened, right? So this already happened. I already took $100 bill out of the bag. How many are left? Well, there's only 4 $100 bills left in the bag. How many bills are there in the bag total? 24, because I took $100 out, right? So now I've got 4 out of 24, and that is going to be reduced down to 1/6. All right? So the probability of A times the probability of B, given A already happened, gives you the probability of A and B. So this would be 1/5 times 1/6, which equals 1/30. So you got a 1 out of 30 chance, which as a decimal, this is 0.033. So as a percentage, this is 3.3%. Right? So if they're dependent, if one changes the other, then you have to take into account that first one already happening, and it's going to change the probability of the second event. All right. Okay, let's take a look at something else here. What do we got? Okay. Comparing independent and dependent events. So we are going to randomly select 3 cards from a standard deck of 52 playing cards. What is the probability that all 3 cards are hearts when A, you replace each card before selecting the next card, and B, you do not replace each card before selecting the next card? We're going to compare the probabilities. All right. So A, we are going to put the card back in the deck after we take it out. We want to get all 3 cards being, what was it? Hearts. So the first question, what is the probability that we will draw a heart? Okay, so probability of event A, right? So if we get a heart, how many hearts are in the deck? Okay, for those of you who don't play cards a lot, there are 52 cards in a deck. 13 of them are hearts, 13 are spades, 13 are clubs, 13 are, what am I missing? Diamonds, right? So this would be 13 out of 52, okay, which does simplify as 1/4. Okay, so that's the probability of getting the first heart. Now we're going to put that back because we're going to place it, so put it back, and now the probability of the second one, probability of event B, is I get another heart. Well, how many hearts are there in the deck? 13 still, right, because I put the first one back. So 13 out of 52, which is 1/4. Now I'm going to draw another one. I'm going to draw 3 cards. So probability of event C. Yes, you can have event C. You could have event D, E, F if you want to do, all the way down to Z and double Z and lots of events if you want. All right. Again, I put the card back, so I still have a probability of 1/4. And this is going to equal the probability of A and B and C. because these are independent events. So that would be 1 over 64, which is approximately 0.016. All right? So that was option A. That was the independent. Now let's take a look at it as dependent events. All right? So, option B. This time we are not going to replace the cards. So the probability of getting that first heart is still going to be 1 out of 4, right? 13 out of 52. 1/4. Probability of that second heart. So this is probability of B given A already happened. So given that we already took one heart out, we no longer have 13 hearts in there. We now only have 12 hearts. And there are only 51 cards in the deck. All right. So now about that third card, right? Probability of C given A and B already happened. Well, now I only have 11 cards in the deck, and that is only going to leave me with 50 cards. 11 hearts out of 50 cards. And this is going to equal the probability of A and B and C. All right. So this equals, stick it in your calculator, and we end up with 11 out of 850, which as a decimal is approximately 0.013. So there's the probability if we replace the cards. Here's the probability if we don't replace the cards. Now it wants us to compare these, so we're going to do this as a ratio. Find out. All right. So what we have 0.016 over 0.013, which is approximately, where did that go? 1.21. So what that means is we are 1.21 times more likely to get 3 hearts if we put the cards back every time. All right. Which makes sense because then there's more cards, more hearts in the deck for those second 2 pulls. Okay. All right. So let's take a look at this next one. Using a table to find conditional probabilities. So we've got a quality control inspector checking for defective parts. Table shows his results. Now, we want to A, find the probability that a defective part passes, so something is broken and it goes through as though it wasn't, and the probability that a non-defective part fails, something that works but it got failed and said it didn't. So let's see what this is. So part A, we want the probability that we pass a broken part. So probability that it passes given that it's already know it's broken. So we want the probability that it passes given it's defective. All right. So what that means is we're going to have the probability that it passes, well, that would be both of these, but it has to already be defective. So it has to already be that one. So we're only looking at the 3. Out of how many defective parts were there? Well, there were 3 that passed plus 36 that didn't. So we've got 3 over 39, which is 1 out of 13. That's the probability. For those of you who like it as decimals, this is 0.077, or as a percent, this is about 7.7%. All right, so that is the probability that something will be defective and will still pass inspection. Okay, so now let's look at it the other way. Question B, the probability that a non-defective part fails. So what we want probability that something is going to fail, all right, given that we know it's not defective. So non-defective. So we want the ones that failed, so we're just looking at these two columns, but it has to be non-defective. So we're not interested in all of it, we're just interested in the 11. Out of how many non-defective parts were there? Well, there were 450 that passed, plus the 11 that didn't. So we're looking at 11 over 461. And that does not simplify, so it's 11 out of 461, which is approximately 0.024, or about 2.4%. All right. So there it is. All right. Last question. We want to find a conditional probability. So at a school, 60% of students buy the school lunch. Only 10% of students buy lunch and dessert. We want to find the probability that a student who buys lunch also buys dessert. Okay, so what this is saying, let's take this. We will have, if you remember our formula, right, the probability of both happening is equal to the probability of the first one given, times the second one given the first one already happened, right? So we have the probability that a student buys lunch times the probability that they buy a dessert given they already bought lunch is going to equal the probability that they buy lunch and get dessert. All right? So let's just see here. Probability that someone buys lunch would be 60%. Put this as a decimal because it's easy to multiply decimals, and percents not so much. Times the probability that they get lunch and dessert. Well, that's what we didn't know. So probability that they get dessert given they already bought lunch. All right, so this is going to equal 10% who get both. 10% of students who buy lunch and get dessert. So 0.1. So the probability that someone buys dessert given that they already bought lunch, right? They buy lunch and they get given that. And so that gives us 0.1 over 0.6, right? Divide both sides by 6, 0.6. And so the probability that somebody buys dessert given that they already bought lunch is going to be 1 out of 6, which is approximately 0.167. So the probability that someone who buys lunch will also buy dessert is approximately 16.7%. All right, so that is a little bit more into probability. Remember, independent events. These are things that happen regardless. Doesn't matter what you flip on the coin the first time, you still have a 1 out of 2 heads or tails on the second one. Doesn't matter. Those are independent. Dependent events, given this thing already happened, what's the odds of this other thing happening? Okay, so that one, they change things. That's like pulling something out of a bag and not putting it back in, right? Picking who plays what position on a sports team, right? If I've already picked Sally to be the center, I can't pick Sally to be something else, okay? So those are dependent events because they change the probability of everything that happens next. Now, in both cases, probability of one times the probability of the other equals the probability of both. Probability of one times the probability of the other equals the probability of both. The difference is with your dependent events, this second probability is going to be changed. Probability of the second one given that the first one already happened. So this one is going to be a little bit different. All right. And that is basically it. I hope that helps. Hope you found it useful, and I'll see you in the next video.